This is a summary of chapters 22 and 23, focusing on 6 types of electric fields. So these 6 types include a point charge or a spherical shell. They share the same equation. The spherical shell condition is that the distance is larger than the radius of the shell. Second, electric dipole. There are three conditions. First has to be dipole. Second has to be along the z-axis. And third is that it's far away from the center of the dipole. Third one is the electric field in between parallel plates, and it's a constant. So these 3 were introduced in chapter 22. And in 23, we introduced a long uniformly charged straight wire. This equation is going to be used very often later on in the next couple of chapters. Then 5 is infinitely non-conducting sheet. So that's a plane sheets with charge. And 6, 2 conducting planes. For example, parallel plates is one example. However, it doesn't have to be parallel plate. It's any surface. It doesn't have to be flat. So the electric field is sigma over epsilon 0. So let's look at the details. Electric field of a point charge. So here the source of this electric field is the charge, as shown as the positive charge in purple color. And the electric field created by it is K times the charge of the source over R squared. So that's from the source to the field. If you bring in a probe charge or test charge, we call the lowercase q, and then you can detect or measure the force exerted on this probe or test charge Q, F. So this electric field can also be calculated as the force over the charge. What's important here is to distinguish what is the source and what is the probe charge. So that electric field equation applies to another scenario, that is to have a shell of electric charges uniformly distributed on it. So we can derive that the shell creates the same electric field outside the shell, and inside the shell, it's 0. The second type of electric field is what we call a uniform electric field. This field is going to be used very often in many chapters forward. So here, the parallel solid color arrows represent electric field. They're parallel, that means they are along the same direction. And if you see they're equally spaced, the spacing represents the intensity. So the intensity or the magnitude is constant everywhere, and you see the direction is everywhere. So as a vector, the electric field is a constant in between the 2 parallel plates. The third type is when you have 2 charges, one positive, one negative, both of same magnitude Q, and they're separated by distance D. If we draw axis Z along these along the line that passes through these 2 points, we call that the Z-axis. So this equation only applies on the Z-axis and only applies to when Z is much larger than D. What does much larger mean? Usually if it's 100 times larger, it's definitely much larger. Even when it's 10 times larger, it's quite larger. But if it's 1 or 2, and then this equation may not give you very accurate results. So these are what the different symbols represent. So those were introduced by Coulomb's law and by experiments. And here's Gauss's law. Gauss's law has these 4 different keywords. It's the net flux of an electric field through an enclosed surface is related to the net charge enclosed in the surface. So this involves a surface integration that's covered in Calculus 3. So I'm just gonna have to explain it using an image that can help you understand this. Epsilon 0 is the vacuum permittivity constant. And that is one of the magic numbers in electricity and magnetism. It's one of the two constants that's used to define the speed of light, which is a universal constant, which represents the limit of our universe. Okay, so to understand Gaussian's law without going through the surface integration, let's imagine there is an imaginary surface. Think of it in the shape of a soccer ball. And so in the center of the soccer ball is your point charge. So this is a tool, it's a utility surface that we put in. Just like when people try to construct a building, they put the scaffolds around it. That helps people to stand on it and build the building. And once the building is completed, you can take that away. Same thing with Gaussian's surface. And people can just imagine the Gaussian surface. What's important here is that when you construct a Gaussian surface, you take advantage of the symmetry. Because it's a point charge, all the points all around it at a certain distance are equivalent. So that is what we call a spherical symmetry. So here E represents the electric field and A represents the area with a direction. So we give a direction to the area, which means it's the direction perpendicular to the surface and pointing outwards. And then we divide the surface into very, very small patches. So this soccer ball is a approximation. It's a small, but it can be smaller. In the real calculation, we make it even smaller, but this is just an illustration to help us understand this. So the flux, if you calculate the flux, what's interesting is the magnitude of the electric field is constant all around the surface, and the electric field is along the same direction as the area everywhere on the surface. So the dot multiplication between electric field E and the area A equals to the magnitude of E times the magnitude of A, because the cosine 0 degree is a 1. If we added up all these small patches, we ended up having the electric field value multiplied by the surface area, which is 4 pi r squared. Rearrange the equation, it gives us the exact same equation as in Coulomb's law. Then you wonder, wait, why do we need Gaussian's law if it gives us just the same as Coulomb's law? Well, this is in the special case of a point charge. When Coulomb's law cannot be directly applied to a long straight wire, for example, so here we use Gaussian's law. We make an imaginary cylinder all around this line. So the electric field around the long straight wire is symmetrical. That means there's not a particular direction that's special. All the directions are the same. Because of that cylindrical symmetry, then these electric fields point towards outwards from the wire if it's positive charge, and inward towards the wire when it's negative charge. One thing I like to point out is we're introducing a new concept that's called linear charge density. We have learned density as mass over volume, that's volume density. So this is a density that's a linear density, meaning the amount of charge per unit length, lambda. The fifth type of electric field is around a surface. So if we have a surface, we're using a flat surface as an example, but if the surface is really large, we don't even have to assume it has to be flat, because when a point is close to a surface, then the surface is automatically infinitely large. So in this case, we make an imaginary cylinder that goes above and beyond, above and under the surface. Okay, then you see the area is A, electric field is E, goes up out of the surface, goes down out of the surface, and all around on the cylinder wall, there's no electric field arrow going out because arrow is parallel to the wall. Okay, so here we introduce another new concept. Sigma is what we call the area charge density, or we call sheet charge density. It's coulombs per meter square. So here, again. So now we've introduced the linear charge density, we introduced the area charge density. And these are new concepts. It's not what we understand as, let's say, the density of water. So I just want to point that out. If we apply Gauss's law, because electricity flow goes out up and goes out down. So the total flow is twice the E times A, that's E times 2A. So that can help us understand that electric field equals to sigma over 2 epsilon 0. The last scenario is we have electric field that is having the charge on one side of the surface. So this can be a parallel plate, and this does not have to be a parallel plate. If we look at one of the plates in the case of a parallel plate, we notice all the charges resides on one side of the metal. So in the case of a metal ball, for example, or sphere, when the surface is also distributed with charge on one side, we can apply this. The condition is that this point needs to be close to the electric field. What's the difference between these two? If we go back to the previous one, we see the electric field goes both sides of the surface. And the only difference between that and this is that the electric field goes out one side of this surface, not the other side. Okay, so because of that, we built a Gaussian surface, then the flow is half of that. As a result, the electric field is sigma over epsilon 0, which is twice the previous one compared to the surface density. So this is sigma over epsilon 0. Okay, in summary, we have learned 6 different types of electric fields, and these fields are summarized here. We especially used, I think, parallel plates and the long uniform straight wires a lot more often. We do need to know the others. All of this should go into your toolbox. Okay, number 1. Number 2, remember condition, condition, condition. So under different conditions, the electric fields will take all these different forms. So you absolutely need to know clearly and accurately the condition for applying each of these equations.